So I quickly recall what was 2 days ago. Basically 4 important things. One was definition of existentially closed model of a theory. So idea was that in this model, all solvable in an extension systems, I just say systems, which means something represented by quantifier-free formula, already have solutions. Just a brief idea what this notion meant. Then there was notion of inductive theory. It was such a theory that all chains of models, for all chains of models, unions of these chains were also models. So. Unions of chains of models are also models. The connection between these two things was that in inductive theories there are lots of existentially closed models of inductive theories. So any model of an inductive theory has an existentially closed extension. And the most important notion was of model companion of a theory. So model companion. Yes, so far under natural assumptions these things exist, existentially closed models, but model companion, you never know if it exists or not. So model companion of T axiomatizes the theory, axiomatizing existentially closed models of T. And this really we don't know what exists or not. Which is kind of true for everything, but here I mean that it's really not clear on the beginning for a given theory whether such a thing exists. Then we have examples. So this was last time. I just write again theory of sets F, model companion. Theory of infinite sets. And theory of linear orders. Also have model companion, the theory of dense linear orders without endpoints. These two are problems for problem session. Okay, and this is the moment when I stopped on Friday.
This T axiomatizes, the mean of T axiomatizes existentially closed models means it describes exactly the class of existential.
Exactly. It means that for any L structure, it is a model of model companion if and only if it's an existentially closed model of T. Okay, so general. Okay, so now something which actually also happened last time, but I will put it into this sequence of examples. So we showed even in two ways that theory of fields have model companion as model companion that, well, it's ACF theory of algebraically closed fields. Okay, so this is all on positive sides. Now I will give 3 more examples, but without proofs, of situations when we have model companion, and then 2 examples with some proofs of situations when we don't have model companion. So, okay, now 2 very important examples, but unfortunately I cannot give any proofs. So one is we start from the theory of fields with automorphisms. So the structure is a field and a fixed automorphism. Okay, so one extra unary functions. Such a fields are called, let's say, difference fields. Yes, a field with a choice of automorphism is sometimes called a difference field. There are some reasons for it. So this one has so you can axiomatize like big or algebraically closed difference fields, and it's called ACFA algebraically closed fields with automorphisms, kind of, but there are more conditions. Okay, and I just say it is. Okay, it has very interesting model theoretical properties. It was analyzed deeply, and there were applications of these properties of this theory to algebraic geometry, algebraic dynamics. There were some classification theorem how definable sets can look like in models, which turned out to be very important. And similarly, okay, the order is maybe not good, even older theory and also very important. So the theory of fields with derivations okay. I mean here one automorphism. Yeah, okay. Not sure what is correct in English, but if I said with fields, maybe I should be saying with automorphisms. But I mean, it's a theory. Each model is a field with one automorphism, and not one with several automorphisms. Several will be also okay, actually, but unless it's a group action. But yeah, I mean, the theory is of fields with one automorphism. Similarly here, the theory of fields with derivations also one, and such are called differential fields. Also have a model companion, and it's also very important. call DCF the theory of differentially closed fields. I can. And it's kind of nicer, it has nicer model theoretic properties, which are also deep, and also there are classification results about definable sets, and it also has, actually it has applications to algebraic geometry and also even to differential equations in a way, to some questions like, there was quite recent, okay, like if you are interested if differential equation has solution in classical functions, whatever it means, exponential, logarithm, etc., and you can, for example, very nicely formalize it in the terms of model theory, and then you can analyze given equation in model theoretic terms, and at the end show, for example, not that some equation don't have such solutions. That's really nice connection of different things.
Are you taking automorphism as a unary?
Yes, one unary function. Here also, so the language here is the same, language of rings plus one unary function symbol. But here the symbol is interpreted as automorphism. Here as derivation, which means Leibniz rule additive. Okay. Yes. So it's kind of, okay, maybe not intuitive, that actually derivations are in a way easier than automorphism to analyze. But okay, it's a bigger topic, but the main reason is the derivation uniquely extends to algebraic closure if you think about it, and automorphism not. And actually that's the reason for model theoretic complications here and a bit easier life here. But okay, this won't be our topic, but just examples.
Is basically the same in the closure, right?
Yes, I mean there is one way to extend algebraic closure if you look at formula. But of course automorphism, as you know by Galois theory, you can extend in many ways. You can extend, but not uniquely. Now something actually which I learned preparing my course in Wrocław. Actually I thought, okay, that's maybe, okay, I should have known better because it's classical. But that's example when I just look at it, at first I didn't know what is the answer. So the theory of commutative groups . Okay, so actually first I thought that it doesn't have model companion. I was trying to show it. And then my proof was my arguments. I noticed my arguments are approaching the direction to showing it has model companion. And then actually I checked it's classical that it has it. So has model companion. So what should it say? You were already thinking last time what should be existentially closed groups. So now commutative groups. Yes, what are the properties which kind of can be expressed by equation in groups? Okay, so one is like saying that if you have element x in a group, you may say there is y such that y times y is x, or y times y times y times y is x. So kind of there are all the roots. So it's divisibility.
Divisible groups.
Yeah.
Because of this inductivity. I was thinking about...
Okay, it's related, but I just directly by definition, like saying that...
What can you say about the language?
Yes. Like for each possible power, you can say there is a root.
Yes.
Okay. Okay, you have to say it somewhere, but it is. You can always find kind of divisible whole. So first thing is, okay, that they are divisible.
You can't write like a very absurd sentence of there exists x and y, x times y times x.
You cannot write strange things, right? It will kind of amount to... So it's like that module, in other words. It's like, okay, like n times x plus m times y, something. But at the end, it boils down to this divisibility, almost. So the theory of course, Yes, divisible comes with commutative, but anyway, divisible groups. And I think you said last time that also orders of elements. So it should have, okay, well, it's good to express it in such a way, so having infinitely many, actually you can say elements for any order, but you may focus on prime orders, so infinitely many elements of order P for each prime number P. And I also say it like this, because I'm not sure if you know, so some comment here.
Can we say that Q over Z is an existentially closed model?
No, because it doesn't, it has just one. Q over Z for each prime P, it has just one element or P minus 1 of order P. Okay, I will get to this if this comment. What a good question. So almost, but it has not, so Q over Z, it is like, okay, this is basically roots of unity in complex numbers. So for each n, you have only n roots of unity. But here you would like to have infinitely many. So that's the reason that not. Okay. But it's pretty close, but not. But actually, okay, maybe you know it's not difficult. What is a structure of commutative divisible group? So if A is commutative divisible, yes, so if you take Q over Z and then infinite direct power, then yes. But okay, so sorry for jumping. Structure is, it is isomorphic. Okay, so what are the main examples of divisible groups? Q and proofer. So Q to some power, these are kappas. And then running over all the prime numbers. So let me define also Cp infinity to some other power, but all as a direct sum. So Cp infinity is proofer P group, which may be sort of as the union. Okay, I like for some reason such notation where Cpn is cyclic of order Pn. So it's cyclic of order Pn embeds to cyclic of order Pn plus 1, and then you can take this union, like before in the inductive theories, and this is proofer, it is divisible P group. Okay, so comment is that this is existentially closed. If and only if all these powers are infinite. But it says nothing about this power, and it cannot say. Yes, you cannot say in first order way. So that's the point I wanted to make. You can talk in first order way about these powers, because basically are saying how many elements of order P are there. So this power is determined really by the Cp part, how many elements of order P exist. But about Q, you cannot say in first order way. It may not exist at all, and it still will be existentially closed.
Looking at the elements that P times that element is equal to 0.
Yes. So this.
Cardinality in first order sentence.
Okay. So this is first order saying okay that exist some big N. Okay, enough to say here such that none of them is 0, and so I use additive notation. So that already says order is P, well, and okay, so this sentence says there are at least n of them, but then I can adding, so I can say there are infinitely many.
You can.
It's enough to say this.
You can write sentences in any coordinate. Is it true?
No, infinite. So I'm only saying it's infinite.
Okay.
Infinite. Yeah, I cannot say it's continuum, for example, infinite. Yeah, I cannot. If you remember, we had this strange example why compactness theorem would fail if I would write infinite conjunction. It happened last month. Yes. That's, so no, it's just here as finite as big as possible, but I just want to say infinite. Okay, so this is the theory. So there is model companion.
There's like a natural model for the existential closed. The models of the theory of existential closure, but not in DCF. Right? In DCF, you don't.
Okay, right. Good point. Neither in ACFA. So here, yes, there are no natural models. They exist. Okay, yes, good point. So, okay. In one, of course, you have natural models, infinite sets, if you believe in infinity. In two, yes, also, like R with order or Q. In three as well, but not so many. Complex numbers, I would say, is the only one. Well, FP-arch a little bit, but it's still just a union. So I would say here there is in nature one natural model, complex numbers. But here we don't really have. So they have to be algebraically closed fields. Okay, in characteristic 0, at least here, with automorphism or derivation, but it cannot be, okay, it exists, but it's not coming from any natural object.
Why you cannot take complex numbers plus automorphism of the complex numbers?
But which one? Which one is the problem?
This conjugation.
No, it's not, definitely it's not a model of ACFA. Huh? Conjugation is not. A complex number with conjugation is not existentially closed. It's even easier of order 2. Yes. And that's automorphism of order 2. And that's something you can say shouldn't happen. Actually, there is a result. Okay, if I'm talking about this. So in characteristic 0, I always forget, but in characteristic 0, models have to have infinite transcendence degree over Q. That can be shown, not so difficult. In characteristic P, actually, you can find on FP-arch. And actually, there are almost all automorphisms of FP-arch with respect to some measure give models of ACFA, but still it doesn't mean you can really show which one, just that there are many. Okay, but yes, so somehow, but still it doesn't really, okay, if you are doing Galois theory, okay, for ease of mind, you can think you are working in complex numbers, but it doesn't change anything. Where are you working? Just that there is something. So. But yes, you cannot give example here. Yeah, okay, so now this negative parts, actually negative examples. So here I didn't plan to give any arguments, but I changed my mind. So the theory of groups does not have model companion. Okay. So I can give full argument, I'm missing the notion of saturated model from model theory and its properties, but I still can give some ideas. The point is conjugacy. So you don't have to look at these crazy formulas you were maybe having in mind. just kind of conjugacy relation brings problems. So let us see. Okay, so first, okay, so if G is an easy group, then as we noticed last time, okay, so now some ideas of the proof, then it has, like here, G has elements of all finite orders. Yeah, that was noticed last time. Okay, but what we will use is that it implies it has infinitely many conjugacy classes, because you cannot, elements of different order cannot be conjugated. Okay, so G has infinitely many and then you show that for some reasons in the SAT, okay, then there is this point I cannot explain properly, but if there was model companion, you could take some big model in other sense, saturated, and that would have finitely many conjugacy classes contradiction. But you will see some ideas. So the point is that now, okay, so like main lemma, the point is that in existentially closed groups, conjugacy classes are the whole orbits of the group of automorphism, which could be much bigger orbit. So if G is EC, then conjugacy classes, so by definition they are orbits of G acting on G by conjugation, coincide with orbits of action of all possible automorphisms. And for the saturated models, such a thing has some description. But let us see that this will be something which is really used. Okay, and of course, yeah, this is something which doesn't exist in commutative case because there are no conjugacy. Everything is trivial. So this can be really a proof. Yes, so we take two elements.
I didn't understand the statement.
Okay,
I didn't understand action.
Okay. So action. I mean, G acts on G. I denote like this. First, by conjugation, like G times X. Okay, what comes first? Let me say like this. Okay, maybe that doesn't matter. And of course, okay, so that makes, yeah, okay. So because of this action, this gives homomorphism to out, but of course automorphism also acts on G naturally. But this is just part of it, yes? So this should have much bigger orbits, but it says in existentially closed now, not the same orbits. So that's very strange. Like, of course, in commutative groups, this has trivial orbits, but there could be lots of other automorphisms, so the orbits are usually much bigger. But in existentially closed groups, not. Okay, so take maybe
it doesn't have any algorithm.
No, it doesn't say so. It says, but the orbits are the same. I mean, it doesn't say anything about them.
Yeah, the orbits are the same.
Orbits are the same. And whether, okay, actually also, guess nobody, these existentially closed groups also exist, but nobody ever saw them, so I don't know what are really the automorphisms, but probably, okay, I don't know. You may be right, but I have no idea, but it doesn't say so. Okay, so take which are in one orbit. So such that, okay, Y is in the orbit. So there is some automorphism F such that f of x is y. Okay, so now we want to show, so aim, that they are conjugate. There is G in G such that okay, but now this happens in a particular extension, which is semi-direct product. So consider, so G is naturally a subgroup. Okay, this acts on G, so we can form semi-direct product. And in semi-direct product, all the action becomes inner, because by conjugation. So here it is true, in all this thing, it is true that there is Z, let me say. Okay, when we consider this x and y embedded here as usual on first coordinate, that so basically Z is equal to this F, which also lives here. Okay, but since G is existentially closed, there is also such a Z in G. Yeah. Okay, so this, okay. So this extension, group extension, was the semi-direct product.
Since G is existentially closed, this Z must be, G Z must
Yes. So this is also equation, yes? This is equation in our language, being in the same conjugacy class. This has a name, I guess, for holomorph?
This is a Frobenius group.
The whole thing?
This whole thing is called a group size with the G semi-direct product, so it's more group.
Okay. Recently I heard something like holomorph, but maybe it was another context. I'm not sure. Okay. But anyway, it's natural.
I want to say something. Let us take x and y from different conjugacy classes. Okay, and then this becomes true. There exists Z in G such that they are in the same conjugacy class. So.
But why it becomes true?
Because of this argument.
But here I know, okay, but what is the F? So here okay. So I'm not sure if I understand, but in this group, this formula is, this sentence is true, because I'm saying what is your Z? Your Z is this F. Okay, in general, there is no reason.
But we are taking G as existentially closed. Okay, and we show that there exists a Z in G such that they are in the same conjugacy class.
Yes, because of this. But under the assumption they were on the same out G orbit, of course.
Okay, then they are.
Yes, so in general. How is it? Still there are groups, but now I again things I cannot remember. Is this Tarski monster group, when I think really all elements are in the same conjugacy class except identity. So maybe we're thinking about this. But I don't think it's Is it existential? Okay, I don't want now to say something. Somehow, I don't think it's existentially closed, but who knows? Okay. Is task existentially closed? I will try to think about it. Okay, so how? Okay, now is the part I cannot explain properly. So here is okay. So general fact for any theory it holds. Okay, so for any L theory, so any theory has this big models. When the notion of bigness is different than this existentially closed, there are the name is saturated. It's still there should be some kappa here. Let me put some kappa, which is big. Models of T. So this is just usage of compactness theorem, such that first the orbits are relatively small. Is it clear notation? This is, so these are orbits. Okay. Group, I mean set divided by action of group, I mean the set of orbits. It's okay, and this M is really, really very big, like cardinality, as big as you want. But this is always bounded by something like this. So like by continuum. So it says it doesn't have too many orbits of automorphism groups. Okay, that's the first property.
What is kappa saturated?
Yeah, that's the thing I'm not saying. Big. Okay, the definition is that that over set of kappa over parameters of size kappa, if you have any system of definable sets which finite intersections are non-empty, then all intersection is non-empty. It's a bit like compactness. So for example, you may see that complex numbers are not like this, because if you have intervals, smaller and smaller intervals, then finite intersections are non-empty, but intersection of all of them is empty. Okay, so like reals are not saturated. But here, and this kappa refers like how much saturated, but you can take kappa, I don't know, like continuum or something, it will be enough here. And then there is such a property that's, okay, kind of it says that if two elements have the same type, we had this notion of type, satisfy the same formulas, there must be in the orbit of automorphism. And there is a bound of number of formulas. So that's the reason, but it requires a bit more theory. But it has another property, kind of, that let's say any definable set in M, let's say to be consistent of cardinality smaller than 2 to the L, okay, so I guess kappa could be maybe this, if you want to know, but don't worry. Is finite. So like definable sets, if they are infinite, they must have big cardinality. There is also kind of bigness, which is maybe more natural. Okay, and we apply it. So now, if theory of groups had model companion T, maybe, okay, just call it T, then we would take saturated model of T. So existentially gross group which is saturated by using lemma, but then so now, okay, by this G, okay, language, now this is really continuum, but how to denote it? Okay, and I'm losing. Okay. Is the same as conjugacy classes. And now another point, and this is like definable. It is a quotient by G by definable relation to which this also applies. So then G out G is finite, contradicting this part.
It's smaller than continuum.
Because here our L is language of groups, but usually by this we mean the size, the cardinality of the set of all sentences. So this is just Aleph 0.
Okay.
So I'll just give something specific, but precise.
So it's not cardinality of L, but...
Yes, it was okay. I think we had the same issue last time. So it's really cardinality of all of the sentences. Yeah. Okay, so this part, okay, was a bit... But somehow the point is that the set of orbits of old G becomes set of conjugacy classes, and this is like something definable. And it's at the same time, okay, relatively small, definable, so finite, but by this argument infinite. And that's the contradiction. So it's not okay. Not very difficult, but also not so easy to find out such argument.
Where did we use it? I mean, why are we using the definability of conjugacy classes?
To apply this part.
Okay.
Yeah, because usually this is not definable at all, but because this automorphism became kind of definable, somehow this is something strange. Okay, so yeah. So I guess this is the moment when one should think, okay, intuitively this should be never a definable object, but it became definable, so we should not be able to apply compactness theorem, but if this theory exists, we can apply it, so it doesn't exist. Such a kind of thinking. That's not okay, but so it needs some intuitions, a bit like that you are able to sense what becomes impossible to express, okay, if such a theory would exist. Okay, so I guess we can have a break now. And